welcome to Mr. Alvarez's virtual chemistry classroom. Today we'll be learning about Le Chatelier's principle. Our aim for today is, what does stress do to a chemical reaction and how does this affect chemical equilibrium? A reversible reaction is a chemical reaction that could occur in both the forward and reverse directions. For example, in the forward reaction we have N2, nitrogen gas, combining with 3 H2s, hydrogen gases, to make 2 moles of ammonia gas, NH3. The forward reaction is a synthesis reaction, 2 reactants combining to form 1 product. We can also put that reaction in reverse. We start off with the 2 ammonia, 2 NH3 molecules, and that can decompose into 1 mole of nitrogen gas, N2, and the 3 moles of H2 gas, hydrogen gas. So if we have a reversible reaction, we can use a double arrow to show that. 1 arrow going forward and 1 arrow going in the reverse direction. Chemical equilibrium is a state in which the forward and reverse reactions balance each other out. That occurs because they take place at equal rates. So when you see the word equilibrium, I want you to think of the word equal. And what is equal in chemical equilibrium? Well, the rate of the forward reaction is equal to the rate of the reverse reaction. Now, that does not mean that the amounts or concentrations are equal, just the rate of the forward and reverse reaction. The concentrations, once you reach equilibrium, will remain constant. So an acronym to help you remember that would be Re, Con. What does that mean? Well, the rates of the forward and reverse reaction are equal. Rates are equal, Re, and the concentrations remain constant. Re, con. The rates of the forward reaction are equal to the rates of the reverse reaction, while the concentrations remain constant. That's when you've reached chemical equilibrium. What does that mean? Well, let's take a look at this diagram. Here we have 4 different flasks. In the first flask, we just have our reactants, so no chemical reaction has taken place. Our reactants, represented by the pink letter A and the blue letter B, have not reacted yet. Over time, when A and B do react, they form the products represented by yellow letter C and green letter D. We start off with 28 A's and 15 letter B's. In the fourth flask, when we've reached equilibrium, we have 11 A's, we have 10 B's, we have 8 C's, and we have 9 D's. Now, we still have more reactants. We have 21 A's and B's than we do products. We only have 17 C's and D's, but we've reached equilibrium because the rate of the forward reaction, so the rate in which A's and B's become C's and D's, is equal to the rate of the reverse reaction, the rate that C's and D's become A's and B's. The rate of the forward reaction is equal to the rate of the reverse reaction, and the concentrations will remain constant. So for every A and B that will become a C and D, well, then a C and D will have to become an A and B. So these concentrations, these amounts, will stay the same within a given range now that we've reached chemical equilibrium. how does this apply to Le Chatelier's principle? Well, Le Chatelier's principle states that if a stress is applied to a system, at equilibrium, the system shifts in the direction that relieves the stress. The secret to life is relieving stress. So let's say in your life, your teachers give you too much homework. The stress on you is the amount of homework that you have. You can't go out and play video games or do whatever you want. So what do? You do the homework so that you can relieve the stress and go out and do whatever you would like. Or the other option would be to not do any of the homework, get rid of the homework. Still, you're relieving the stress on you and you can do whatever you would like. A stress in a chemical reaction is a change in a system at equilibrium that disrupts the equilibrium. For example, a seesaw. So if you start out even on a seesaw and one person goes down, the other person is going up. They're no longer at equilibrium. So the person on the left has to use their leg muscles to push up and shift the equilibrium. Now the person on the right is down on the ground. They have to use their leg muscles to relieve their stress. They push up and it goes back and forth till they're finally done and they reach equilibrium. A biological example of Le Chatelier's principle actually happens in your body. And it has to do with how your body handles temperature change. So, if this is the normal temperature of your body, and you are running around or exercising or it's just hot out, your body temperature is going to rise. That is the stress placed on your body. So in order to regain equilibrium, your body is going to sweat to bring the temperature down. Now if your body temperature is too low, maybe you're outside and it's cold out, your body is going to shiver to bring itself back up to equilibrium. So no matter what the stress is applied, your body is going to do the opposite to bring itself back to equilibrium. If it's too hot, your body's going to cool itself down. If your body is too cold, it's going to warm itself up so that you regain that level of equilibrium. In biology, that's called homeostasis. Chemical systems function in a similar way. We are going to take a look at a reaction at equilibrium and see how different stresses affect that rate of reaction. The first stress we're going to look at is changes in concentration. If we add reactants, we are going to increase the rate of the forward reaction. So for example, we have this reaction at equilibrium. We have carbon monoxide gas plus hydrogen gas goes to methane gas plus water vapor. If we were to add more of a reactant, more carbon monoxide gas, you've just taken the system out of equilibrium. The system, wanting to be back at equilibrium, is going to shift the reaction to the right. We are going to try to get rid of all of the extra CO that was added. And how do we do that? We are going to make more methane, CH4, and more water vapor. As a result, we are going to decrease the amount of hydrogen gas. A more real-world example would be, let's say that we own a bike shop. And for simplistic purposes, let's say to make a bike we need one frame plus 2 wheels makes one bicycle. Let's say we just get a whole shipment of frames in, so many that we have nowhere to put them. We are a bike shop. We sell bicycles. So what we could do is, if we have too many frames, we can take those frames and take the wheels, shift the reaction to the right, and make more bicycles. As we do that, the number of bicycles increases, the number of frames decreases because we're using them up to make the bicycles, and as a result, the number of wheels decreases as well to make the bicycles, to get us back to equilibrium. So we have room in our shop. In the chemical reaction, the reaction shifts to the right when you add a reactant. More product is being reduced. Here we had too many frames. We shifted the reaction to make more bicycles, so the product, the number of bicycles, increased as the number of wheels and frames decreased. Adding more CO or H2, back to our chemical example, will shift the reaction to the right and produce more CH4 and H2O, more product. I want you to write something down. Add, away. If we add more of a reactant, we are going to shift away. The reactants are on the left, so we're going to shift to the right, to the product side, to decrease the amount of reactants, and that'll result in an increase in the amount of products. The opposite is true if we remove reactants. If we remove reactants, the rate of the reverse reaction is increased. The reaction shifts to the left. So, if we were to decrease the amount of carbon monoxide gas to the same reaction at equilibrium, the reaction is going to want to shift left to make up for the lost carbon monoxide. So, what does the reaction do? The reaction breaks down CH4 and H2O and makes more CO to get back to equilibrium, and as a result it makes more H2, hydrogen gas. So the amount of products in this case, when we remove a reactant, the amount of products, CH4 and H2O, decreases, while the amount of H2 and CO increases. Back to our real world example, let's say that a customer comes in and they need a frame for their bicycle. For some reason, the frame on their bike is bent or broken. We don't have any more frames. We do have bicycles. So what we can do is we can take the bicycles and use them for parts. We can decrease the number of bicycles, and that would increase the number of frames and the number of wheels. So we have that frame to sell to that customer. We shifted the reaction to the left to make more reactant in this case. I want you to write something else down. Take towards. If you take something away, if you remove something, the reaction is going to shift towards the item or chemical that was removed. So in summary for this reaction, removing either CO gas or H2 gas will shift the reaction to the left to replace what was lost. So CO and H2 will increase as a result, and CH4 and H2O will decrease. Once again, you're using the CH4 and H2O, you're breaking them down to make more CO and H2. Let's take a look at the other side of the reaction. If we add products to a reaction at equilibrium, the rate of the reverse reaction will increase. The reaction will shift to the left. Remember, add, away. This time we're going to the right side, the product side, and if we increase the amount of H2O gas, if we increase the amount of water vapor, the reaction taken out of equilibrium is going to shift to the left. Add, away. We're on the right side. We added something to the right side, so we're going to shift away to the left side. So what's going to happen? The H2O and the CH4 will recombine to make more H2 and CO to get rid of the extra H2O, and as a result, it'll decrease the amount of CH4 as well. More reactant was produced, and the product is going to decrease. So in summary, adding more CH4 or H2O, the product, will shift the reaction to the left. If you add, you go away. Start on the right side, add away, go to the left, and produce more CO and more H2. Back to our real world example. Let's say we have too many bicycles in our shop. We have no room on the show floor to display them all, but we can take them apart and store them as parts. So if we have too many bicycles, we can take them apart, decreasing the number of bicycles, and then as a result, we would increase the number of frames and wheels in our stockroom. Our final change in concentration comes when we remove products from a system at equilibrium. When we remove products, the rate of the forward reaction is increased, which means the reaction shifts to the right. So in this equation at equilibrium, if we were to remove a product, let's say H2O, the reaction will shift to the right to make more H2O. We lost H2O, the reaction shifts to the right to make more H2O. Remember, take towards. By removing the H2O, by taking away the H2O, we are causing the reaction to shift to the right to make up for that lost H2O. How does that happen? The CO gas will react with the H2 gas to produce more H2O. As a result, more CH4 will be produced, and as a result, there will be a decreased amount of H2 gas and CO gas. So the CO and H2 are used up to make more H2O, and as a result, we make more CH4. Back to our real-world example, back to our bike shop, let's say we had a huge sale on bikes, so our amount of bikes decreased, but being good shop owners as we are, we need more bikes for the showroom. How do we get more bikes? Well, we shift the reaction to the right, take towards to make more bikes. By making more bikes, by increasing the amount of bicycles, we are decreasing the amount of frames and the amount of wheels. We are using up the frames and the wheels to make the bicycles. So, in our chemical reaction, by removing either CH4 or H2O, either of the products, that will shift the reaction to the right, take towards, to replace what was lost. As a result, the concentration of the reactants, in this case CO gas and H2 gas, will decrease. Another factor that would affect a system in equilibrium is temperature. Let's start off with an exothermic reaction. Remember, an exothermic reaction is a reaction that releases heat. Heat is exiting from an exothermic reaction. I know that this reaction is an exothermic reaction because the heat is on the right side of the reaction. Heat is on the product side of the reaction, which means heat is being released. Now, I want you to treat heat as you would any other substance, just like we did in the last section. Remember, add away. In the first example, we are increasing temperature. By increasing heat, by adding heat, we are going to shift away. So in this case, since the heat is on the right side, by adding heat, we are going to shift away to the left side. As a result of this, the substances at the tip of the arrow, the CO and the H2O, will increase. The concentrations of the reactants will increase. Also, by shifting the reaction to the left, we will decrease the amount of CH4 and H2O. By shifting the reaction to the left, we're making more H2 and CO by using up CH4 and H2O. These will decrease, the products will decrease, the reactants will increase. The opposite is true if we were to decrease the temperature. Remember, take towards. If we are decreasing temperature, we are taking away heat. So the reaction would shift to the right towards the heat being lost. As a result, the tip of the arrow would increase, so the amount of H2O would increase, the amount of CH4 would increase, and the reactants, CO and H2, would decrease. The reaction shifts to the right when you decrease temperature, take towards. So CO and H2 would decrease, while CH4 and H2O would increase. Let's take a look at an endothermic reaction. An endothermic reaction is a reaction that absorbs heat. An endothermic reaction, heat enters. Heat goes in an endothermic reaction. We know that this is an endothermic reaction because the heat is on the left side. Heat is on the reactant side. Heat is being absorbed, going into this chemical reaction. So, if we increase the temperature, remember, add away. If we increase temperature, we are going to add away and shift to the right. At the tip of the arrow, those substances will increase, so NO2 will increase, and the substances at the tail of the arrow, the N2O4, will decrease. We increase the temperature, we shift the reaction to the right, which increases the NO2 and decreases the N2O4. If we were to decrease the temperature, if we remove heat, we're going to use the rule of take towards. If we remove heat, which is on the left side, we are going to draw the arrow towards the left side. As a result, the tip of the arrow, N2O4 will increase, and NO2 will decrease. Our final factor that affects systems in equilibrium is pressure. Now, pressure only affects gases. Changes in pressure, if you have a reaction of gases and the number of moles on the reactant side is different from the number of moles on the product side, the reaction will favor the direction in which there are less moles. Think about pressure in your own life. Let's say you have a big final exam coming up. There are two rooms in which you can take this test. There's a room filled with 100 students or a room filled with 2 students. You get to choose. You're probably going to choose the room with 2 students. Since there is more pressure, you're going to want a quiet space, a room where you have plenty of space to work. After the test is over, after the pressure is gone, you're going to probably want to go to the room with 100 students to hang out with them. It's similarly true for gases. Let's take a look at this reaction, in which we have only gases. We have, once again, CO gas plus 3H2 gas goes to the products CH4 and H2O. We have to count the number of moles. We do that by counting the coefficient. Now, CO does not have a coefficient, so it has an imaginary 1 in front of it. H2 has the 3 as a coefficient in front of it. So 1 plus 3 is 4. So we have 4 moles on the left side, on the reactant side. On the product side, once again, no coefficient, so they have an imaginary 1 there. 1 plus 1 is 2 moles. If we were to increase pressure on this system, it's going to shift to the side with less moles. 4 and 2, obviously 2 is a smaller number. So if we increase pressure, the reaction will shift to the right. If we decrease pressure, it's going to shift to the side with the more moles. 4 and 2, 4 is a greater number. So if we decrease pressure, the reaction will shift towards the left. In summary, there are 4 moles of reactants and 2 moles of products. Increasing pressure is going to shift away from the more moles towards the less moles. So increasing pressure is going to shift to the right in this case. And decreasing pressure is going to shift towards the more moles, shift towards the left in this case. Let's try some practice problems together. The directions state, predict the direction equilibrium will shift when the following stresses occur. Explain your prediction. Assume each reaction occurs in a sealed container and has reached equilibrium. The reaction is 2NO2 gas goes to N2 gas plus 2O2 gas. It also tells us the delta H is a positive 33 kilojoules per mole, which is an endothermic reaction. Well, I'm going to put the energy, the heat, on the left side because it is an endothermic reaction. Heat is being taken in. So it goes on the reactant side, 33 kilojoules per mole. Now let's take a look at some of these problems. Problem number 1 says NO2 is added to the system. Remember from before, add away. I find NO2, it's on the left side. Add away, if I'm adding to the left side, I'm going to shift away to the right side. So the system shifts right. For number 2, it says N2 is added to the system. Once again, add away. I find N2, it's on the right side. Add away, I'm going to add away from the right side, so it's going to shift to the left. Add away, start on the right, shift to the left. The third one, O2 is removed from the system. We have add away and take towards. O2 is removed, O2 is taken away, take towards. Since O2 is on the right side, we're going to go towards the right side, so equilibrium is going to shift right. Number 4 says that temperature of the container is increased. Remember, treat temperature, treat heat as you would any other substance. Since the kilojoules, the heat is on the left side, we're increasing temperature, we're adding heat, we're going to shift away, add away. Since the heat is on the left side, we're going to shift away to the right side. So if we increase temperature, we shift to the right. Number 5 is a tricky one. It says the volume of the container is increased. Now remember from Boyle's law, pressure and volume have an inverse relationship. For pressure, if you remember, to figure out pressure, we have to count the number of moles. On the left side, we have 2 moles of NO2. On the right side, we have imaginary 1 plus 2. We have 3 moles on the right side. So if we are increasing volume, that really means that we are decreasing pressure, according to Boyle's law. So if we are decreasing pressure, we are going to shift to the side that has the less number of moles, which is the left, so we are going to shift left for number 5. Finally, number 6 states N2 is added and NO2 is removed. So if N2 is added, add away. N2 is here on the right side, add away. We're going to shift left. And NO2 is removed, take towards. NO2 is on the left side. If we're going to take towards, we're also going to go to the left side. So both of these situations tell me that we are going to shift left. Thank you again for joining Mr. Alvarez's virtual chemistry classroom. Today we learned about Le Chatelier's principle and how it relates to systems in equilibrium. Equilibrium, remember, re, con, con. Re, the rate of the forward reaction, is equal to the rate of the reverse reaction. And con, con, the concentrations of reactants and products are constant. Rates equal, concentrations constant. We also looked at what would happen if we stressed a system at equilibrium. We saw what would happen if we change the concentration, we change the temperature, or if we change the pressure of a gas. Remember, add away, take towards. Thank you again. I hope you have a wonderful day. Bye.